Welcome to all the listeners, all the participants. I welcome you all on behalf of University of Engineering and Management, UEM Jaipur ACM Student Chapter. So the UEM Jaipur ACM Student Chapter and the Department of Computer Science and Engineering, UEM Jaipur, in association are organizing this distinguished lecture, Eminent Speaker Program, I should say, a webinar by Professor Dr. R. Ramanujam. Professor Dr. R. Ramanujam is a professor of Institute of Mathematical Sciences, Chennai, and today he is going to talk on the topic, why should we learn algorithms and why should we learn algorithms? It is interesting, why should we learn algorithms and why should we learn algorithms? Actually, it is why should we learn algorithms and why should we learn algorithms? So, because this is being conducted by ACM, UEM Jaipur ACM Student Chapter, I should talk about ACM firstly. The Association for Computing Machinery, ACM, is the world's largest scientific and educational society through different local chapters, amongst which our UEM Jaipur ACM Students Chapter also stands strong. ACM delivers resources that advance computing as a science and a profession. ACM provides the computing field's premier digital library and serves its members and the computing profession with leading-edge publications, conferences and career resources. ACM brings together computing educators, researchers and professionals to inspire dialogue, share resources and address the field's challenges. As the world's largest computing society, ACM strengthens the profession's collective voice through strong leadership, promotion of the highest standards and recognition of technical excellence. ACM supports the professional growth of its members by providing opportunities for lifelong learning, career development and professional networking. UEM Jaipur ACM Student Chapter was founded in the year 2014, and from then onwards the students are all giving their best to perform the duties of an ideal student chapter. I would like to take this opportunity to extend a very warm welcome to our beloved guest, Honorable guest, Professor Dr. R. Ramanujam. Professor Ramanujam got his BE Honours in Electrical and Electronics Engineering from BITS Pilani and his PhD in Computer Science from Tata Institute of Fundamental Research, Mumbai. After postdoctoral research at the City University of New York, he has been at the Institute of Mathematical Sciences, Chennai, where he is currently a professor. His research interests are in mathematical logic and theory of computation, and their applications to theory of distributed systems, game theory and security theory. He is currently on the editorial board of ACM Transactions and Computational Logic. In 2010, he was Lorentz Fellow of the Royal Netherlands Academy of Sciences at the Netherlands Institute for Advanced Studies. He has been actively involved in the Indian Association for Research in Computing Science and the Association for Logic in India. I really believe that's a big profile, and in fact it is half of it. If I would have read the whole thing, it would be taking a lot of time. Sir, I won't waste any more time. I hand it over to you. It is really an honor for us that you have come over here and you have agreed to talk to our students and our teachers. We are really waiting to hear from you. Thank you, sir. It's all yours from here. Thank you.
And computer science teachers as well. And I thought this is something that I would like to have with you. So I don't mean it as a formality. Please do interrupt. Please do ask questions. You can raise your hand. I'm sure if the moderator will let you ask questions if required. So it's part of the freedom that you have. And I was very happy to hear about this institution, and I'm very happy to be part of this webinar today and to have this wonderful opportunity to meet you all. So it's a pity that these times we can't see each other and sit together in a seminar and do. That's part of academic life. Unfortunately, this huge disruption has caused something where we have to talk like this. But it's also an opportunity because how many times, how many places can one travel? This is something that gives me this wonderful opportunity that with the ACM webinar. I'm very happy to be with you today. So I'll start the discussion. Let me share screen. So the title I have given is really why should we learn algorithms, right? But then why is it repeated twice in the poster, right? It's really only one. Why should we learn algorithms? Now, before I think I don't have a single answer to this, but I think this is something I would like all of us to think about. Algorithms is a compulsory subject in computer science, and all bachelor students go through some algorithm. Now, why is it there? I've been on board of studies of some universities, and once, in fact, the way this happened was that I had gone for a board of studies meeting at a central university, after which I had been invited to have an interaction with students, and I went for the interaction, and I asked people, do you know what I'm here for? People said, they know. I said, it's a board of studies meeting. Turned out that most of the students had never heard of board of studies, and why should they know? I mean, it's usually faculty, only top faculty, maybe vice chancellor knows boards of studies, but normally. So I said, yeah, this is where we decide curriculum. We decide what are compulsory subjects, what are electives, all this kind of thing. And so I then we discussed what are the compulsory subjects. In computer science, I asked, is it algorithms compulsory? And it turned out that it was compulsory. And so I asked everybody, why should we learn algorithms? And I found that very few students or faculty answered that. So I said, come on, we cannot accept something like this. Something is compulsory and we have to do it. We should know why we are doing it, right? That started off the discussion. After that, I've had this kind of discussion many times, and always many interesting points come up. And I thought this an opportunity when I got this lovely invitation. So I made it very clear that I want to use this opportunity to have this discussion with all of you. So thank you for it once again. So before we start, here are some words. Here's a quotation. Let me read out the quotation. It says, we should explain before proceeding that it is not our object to consider this program with reference to the actual arrangement of the data on the variables of the engine, but simply as an abstract question of the nature and number of the operations required to be performed during its complete solution. Somebody has written this. From the English, you can make out that it's kind of old way of writing. But somebody is talking about a program and data and so on. Can anyone guess who it is by? Anybody wants to try? Who said this?
Anybody who wants to answer, kindly unmute yourself and answer.
Or raise a hand. Yes? Yeah. Somebody said something? Okay. This is actually the Leda Augusta Byron King, Countess of Lovelace. So she was the world's first programmer. And this is the year she's writing. Look at the year, it's 1823. Long before computers, long before electronics, so on. And she was talking about programming Babbage's differential engine. In fact, so she wrote a program. As I said, the world's first programmer was Ada Lovelace, a woman, young woman. She's the daughter of Lord Byron, a famous poet. And she was writing a program to solve a differential equation. Now, I don't know how many in this room, the people here, have written a program to solve a differential equation. It's not an easy thing to do. And she was talking about doing that on a machine which is mechanical and which was not built. She didn't have an actual machine to run the program on, but she was writing the program. And already she says, it's not our object to consider this program. Of course, you're arranging the data on the variables, and but much more important, you have to think about it as an abstract question of the nature and number of the operations required to be performed during its complete solution. So Ada is speaking to us across 170 years, 177 years now, and reminding us that every time you are writing a program, the underlying algorithm is the most important. And what is very important here is that almost 150 years later, in 1990s, the University of Manchester actually built Babbage's engine, the analytical engine and the artificial engine, according to the specifications, and ran ADAS program, and it worked. So that's something phenomenal that you should think about. Because when you write a program, I don't know how often you actually go to it, compile it, and it works immediately. This is a really difficult thing to do. So she's giving us a very important insight that we should listen. Okay, so here are the questions that I would like answers to. Algorithms is a compulsory subject in computer science in every course. Why should we study these algorithms? What are algorithms? These are techniques. We all know lots of algorithms. When you learn any computer science at all, you learn sorting algorithms, searching algorithms, do something in a graph, finding a cycle in a graph. You find a lot of algorithms. Why should we study these algorithms? My second question is, if I'm a student and I joined a computer science program in this institution, let's say, why should I study algorithms? You know, it's okay. First, you may say algorithms are important, therefore we should study them. Why should I study it? Let somebody study it. I don't, I want to complete my degree, get a job, work in a software company, or, whoever is giving me a job, right? Why should I study algorithms? Why is it compulsory? Another question. Well, if I'm going through an algorithms course, I'm a reasonably sincere student, and I put in my assignments, and I do my homework, and I learn. What can I expect to learn from this algorithms course? And so these are important questions in mind. And these are things not to be taken for granted. The honest answer that I see, we learn algorithms because it's a compulsory course, right? I don't have an option. Why do I study theory of computation? It's a compulsory course. I don't have an option. It's something that I have to go through in a particular semester. I have to get a certain grade, and without that grade, the university is not going to give me a degree. Therefore, I do it. It's not because I'm convinced that it's important, and nobody has told me why it is important. And okay, it is important. And again, important for what? I mean, important for my getting a job. Maybe if I get my web management skills better, I may get a better job. Why should I bother with that? Right? So somewhere that it is considered a core subject in computer science, you have to ask, why is it a core? And the other thing is, if I go through an algorithms course, what are the skills that I expect to acquire? Can you ensure that I have acquired that skill? What should I do to acquire that skill? So what is it that we are really expecting from an algorithms course? So this is really the point of this discussion. Once again, let me repeat, it's not that I'm having some particular answers that I want to send here. I want everybody to think about this. Ideally, all teachers should make up their own answers and all students should arrive at their own answers. That is what is the purpose of education. Fortunately, we never get there, but I thought, we have to start thinking about this. So I hope that by the end of this talk, all of us can have some answers to these questions. It cannot be uniform, but I want some answers. But before that, I have another question. And this is a question that I want you to answer. Well, we have a degree in computer science. Dr. Chatterjee, is the degree called computer science or computer science and engineering? Or what do you call your degree?
So we call it computer science and engineering, BTech in computer science and engineering.
Excellent. So it is computer science as part of the degree. Right? Now, my question is computer science really a science? Now, we all learn science is a compulsory subject in school, and everybody learns science. Now, what distinguishes science from all of the subjects in school? What is unique about science? Can somebody try to answer this? And then you have to explain to me why computer science is a science.
Science uses the scientific method, the scientific methodology of hypothesis and experimentation to arrive at a conclusion, at a, basically at some tentative view of the object of study.
Wonderful. Thank you so much, Mr. Basu, right? Yeah. I completely agree. So if there is one thing that distinguishes science from all other disciplines of study, that is experimentation, right? I mean, every subject, every discipline has its own way of arriving at the truth, right? Mathematics, the standard of truth is proof. What you accept in mathematics is whatever you can have a proof for. In science, and this is very important in these days of COVID, when all kinds of fake news is floating around, all kinds of junk is floating around, how do you know something is true? Well, science is you accept only what is verified by experiment. The emphasis on experimental verification. And as Mr. Basu pointed out so beautifully, it is about, there is a process of science. You form a hypothesis, you perform an experiment, and if by repeated, and you don't do it once, right? You learn in your lab that you have to repeat the experiment many, many times, take average because there can be a lot of error, allow for all of that. And then what you understand is what you accept as true. I don't see any experimentation in computer science. How is it a science? That's precisely my question.
Running the algorithms on the computer, that is the experimental proof of the algorithms.
I want to know more about Indranil Basu now.
Yes.
Are you a teacher or are you a student?
I'm a teacher in IEM, Kolkata.
Okay. It's wonderful to have you, sir. Now, what about the students? Is there a student who thinks that computer science is not a science, or is it a science? Would any of the students like to express an opinion? Yeah. Let me ask this way. A computer is a machine after all. Yeah. Of course, we have no doubt about it, right? A computer is any machine. Yeah. I want to hear. Yeah. Somebody wants to say? Who's that? Yeah, so I see one thing on the chat box where Somit Biswas says science deals with natural phenomena, whereas computers are man-made, so it is artificial. Absolutely. That's why I said it's a machine, right? And so what is a machine science then? Can we have the elements of a machine science? I've never heard of a machine science, right? The fan that's rotating above my head, that's a machine. This computer that I'm using, the laptop, that's a machine, right? The tube light is a machine. These are all machines.
The machine is a product of computer engineering.
Yes.
But the algorithm is a part of mathematics because it is a study of the process by which we arrive at a solution, or basically we are a process to be solved. And the experimental verification of the algorithm is done by using that machine, just like you use a CERN accelerator, which is a machine for particle physics or theoretical physics.
Yes, but there the experiment is to verify some hypothesis. Yes. But in the case of an algorithm, there is no hypothesis to verify. In fact, you want to prove the algorithm.
Yeah, so
now I want to come to this a little later. But the point I'm making is that it's a piece of mathematics somewhere. Finally, you have a dabba, a machine, and somehow you call it a computer science. Now, what? So let's step back a little bit. I've never heard of a fan science, right? Mic science, tube light science, right? And I've never heard of a machine science as such. We do talk about mechanical engineering. We don't talk about a machine science, but we talk about computer science, right? We have all degrees in computer science. Is there something distinctive about this particular machine so that we can even something special about this machine so that we can talk about that particular machine computer as a computer science? What is special about a computer as a machine that lends itself for us to even formulate a science based on that machine. Now, one thing is that it's remarkably versatile. Probably it is one of the most versatile machines that humanity has designed. Right? Now, I don't know how many people here have seen a lathe. Now, when I studied engineering in BITS Pilani, I went to the workshop and I learned and I learned to handle a lathe. Now, a lathe is something phenomenal. It was like a stunning thing for me because you could, engineers here would know about it. And anybody who has done any mechanical engineering has really played around a lot with a lathe. A lathe is a wonderful machine. And for anybody who has not seen, I would strongly advise them to go and look at it. A lathe is where you take a piece of wood, typically a piece of metal, completely misshapen looking metal, and then you do various processes with it. You do milling, you do grinding, you do all sorts of things, and you can produce a beautiful flower vase. What makes it so? And today, lathes are programmable. Right? And wooden lathe, you can take a piece of wood which looks like nothing on earth and actually produce a beautiful chair. Now, so it's a remarkably versatile machine, but I've still not heard of a lathe science. Right? Now, somehow a computer is more versatile in all this, more programmable than all this, and somehow is able to give us a capability that goes well beyond all of these. What is that? And that's very important to understand the soul of this subject, I would say. In fact, one machine that I like very much is something that we find in all our homes. Right? And this is the pressure cooker. The pressure cooker, everybody knows it. We don't have to go to a lathe. What does it do? You put stuff inside, you put the lid on top and then the weight on top, apply heat, and after a point, pressure builds up. That thing goes, makes noises, releases the whistle, and pressure comes out, and after a while, it cooks inside. Well, no heard of a pressure cooker science, but I want to have a proposal to have a pressure cooker science, and a proposal goes this way, right? What is a pressure cooker science? It is that I look at the pressure cooker and start looking at everything in the world as those which I can actually cook using my pressure cooker and those which I cannot cook. Now, what are all the things that I can cook in the pressure cooker? Well, I cook vegetables, I cook chicken, I cook pretty much all these things. What are the things that I cannot cook using my pressure cooker? Anything that I cannot cook? What about a piece of wood? If I put a piece of wood in a pressure cooker and try to cook it, will I be able to cook it? Yeah. What about a piece of metal? Will I be able to cook metal on? Does anyone have anything to say?
Sir, what we eat, we can cook everything in pressure cooker.
Yeah. So, well, basically what I'm saying is that you are now able to take the pressure cooker and what you are looking at is not the pressure cooker at all. You are looking at things in the world. Right? You are looking at things in the world and you categorize them as those that can, that are cookable and not cookable, so to speak. Right? Those that can be cooked and those that cannot be cooked. So, in fact, if you put your finger, of course, it gets cooked, right? And meat gets cooked, wood gets little bit cooked, metal does. And the main thing is that anything that has water content, that's the process of cooking, right? If there is some water in it, the water evaporates and things get cooked. So wood has some very faint amounts of water, and therefore it cooks a little. Metal doesn't have any water and it doesn't cook, and that's why you're able to use the vessels at all. Now, what have you done? You're now, as I said once again, your object of study is not a cooker at all. Your object of study is things in the world, and you're categorizing them. Now, you can go further and ask, I have my pressure cooker, which cooks faster, dal or potato? Yes, Anurag Kumar, what do you think? Which cooks faster, dal or potato or chicken? Anybody else wants to answer?
Dal, sir.
Sorry, I couldn't hear.
Dal.
Okay. And then what is the ordering among them?
I don't know the ordering right now.
Ah.
Potato then chicken.
Ah, great. Okay. And what about other vegetables? What do you think? And the point is this: how long does it take actually doesn't matter. Because suppose tomorrow I have some super duper technology, and in fact I go to a microwave, right? Now, in terms of how much time I get, yeah, I see some ordering given dal, potato, chicken, right? Now, the ordering is very important because the amount of time it takes on a pressure cooker to cook some certain amount of dal, certain amount of potatoes, certain amount of chicken is not going to be the same when you use a microwave. Or tomorrow some super duper infrared technology comes and you cook, the numbers will change. What will not change is the ordering. That dal takes more time than potato. No, that because it has a property of the objects that you are talking about. It has nothing to do with the technology that you are using. The technology could be pressure cooker or microwave. So this is precisely what makes computer science a science. You are using the computer as a tool, and what you're looking at are problems in the world, and you are categorizing them as those that are solvable by the computer and those that are not solvable. We call it decidable, undecidable, all that doesn't matter. Solvable and solvable. That's a categorization. And then within the solvable, you go to you say, these are the things that require more resources and these take less resources. And we say it in a technology independent fashion. And this is extremely important for computer science students to understand that when you say science, you are making technology independent statements. Sorting, I want to say how much time it takes, but I want to answer it in a technology independent fashion. I don't want to say it in terms of the computers that existed yesterday or the laptop that I use today, or no, I want to make a statement that will hold in the year 2120. Independent, by then maybe people will be using quantum computing. I don't care. I want to talk about statements that are technology independent. And there, what you are studying is not the computer at all. It's problems in the world, like you're talking about cooking. This is the study of algorithms and complexity, where in a pressure cooker, you use the pressure cooker as a tool to analyze things in the world. You categorize them, classify them. Classification is the beginning of science. Solids, liquids, gases, living, non-living, all that, right? And that's why we call it a science. You develop a whole categorization. Now, there is a lot to discuss in this. I don't want to go on with this, but I want to point out that you can discuss it externally like what we did. You simply use it as a tool to go and study, or you can take a pressure cooker and look at, write differential equations to see how the pressure goes up and down and the process of cooking happens. That's a study of programming languages, study of hardware, where you go into the details of the machine and how the machine states are transformed. We call it theory of computation or right? And so the technology independent aspects are the core of what we would call the science in computer science. And it is a science of the artificial, it is not a science of the natural. And you create artifacts, but what is extremely important is that you are making statements that hold for all time, as opposed to the engineering aspects. So these are the two paradigms of computer science that I wanted to introduce. One is the paradigm of algorithms and complexity, where you use the computer as a tool to go and study problems. And you say they are hard, they're easy, or this is harder than the other, the dal, potato, chicken kind of ordering, right? And the other paradigm is the theory of computation, programming languages, where you go into the internals and study. And today's talk, we are only looking at the algorithms. Now, I said hard and easy in the classification. But what is easy? What is hard? Because what is hard may be easy for you, and what is hard for you may be easy for me. And what is hard for me, what was hard for me 5 years ago is easy for me now. And what was very easy for me 10 years ago, I find hard to me now. So it's a function of whom you're talking to and when and what you had for breakfast, etc. So how do you say in a scientific manner what is easy and what is hard? So here is a question: what is the hardest problem you ever solved? Does anyone have? I'm talking about personal lives. Right? In your personal life, what is the hardest problem you have solved? Does anyone want to say anything? Any statement at all is okay. I want to hear somebody's opinion on what they consider very hard.
So basically, why we do need to give more effort than any other problem is the hardest problem.
No, I'm asking you personally, in your life, whatever problems you have solved, what is the hardest one that you have considered, that you consider to be the hardest? And these need not be mathematical problems. It can be a problem in everyday life.
It is difficult to answer.
Well, I would say getting two small children ready for school in the morning at 7 o'clock is one of the hardest problems I have solved. Right? To give an indication of what we. So, see, it's really a matter of difficulty is a matter of your time, circumstance, resources, everything. Right? So, yeah, somebody was saying something? So the main point is that we need some way by which we can talk about, if we want to do this classification in a technology independent fashion, we have to get rid of all this fact that hardness isn't something very different, easier for people, and it may be a function of time. So we are not talking about difficulty here. In natural language, in most Indian languages and in English, we do not distinguish these two terms. We do not talk about something being difficult. In mathematics, there are many difficult problems, right? And if I give you a very large number and ask you to find its factors, it's difficult. Is it hard? Is the question. Hardness that we are talking about is something that I want, which is independent of who's trying to solve and when. And as I said, I want to come up with a classification that will hold in the year 2120. Right? So it should be completely technology independent. Now, this is very hard because you've got a certain tool that you want to use, and you say that I want to use the tool and use it to, solve, and then you say that I should not refer to the tool at all because the technology will change. So that makes it a very beautiful mathematical question. Now, here is a question that I want to ask. And, everybody uses some public mail system, say Gmail, yeah? And what happens when you log in? How do you log into your Gmail? Gmail or Yahoo or anything. Yeah? Somebody tell me, how do you log in?
So using my ID and password.
Correct. You use your ID and password, right? Now, how is it sent on when you type in your user ID and password? How is it sent on the channel? Can I, by watching the channel, get hold of your ID and password? It's being sent to the server, and I now sneak in between, and I see what is going between you and the server, and can I get your ID and password? Does anyone have an answer to that?
I can please ask again, sir, because I don't understand what you want to.
So like trying to get someone else's ID or like.
No. I'm saying you are typing in your password, and it is being sent to some server, right?
Yes, sir.
I'm watching the channel, and then can I get your password?
Sir, you can get, but it will be in the encrypted form.
Ah, that's the point. It's an encrypted form. It's a code form. But how does the encryption work then? Encryption works by coding it up, right? Now that is what we call a one-way function. A one-way function, encryption works using one-way functions. What's a one-way function? Well, you take any x, applying the function f of x is very easy. It's like a lock. But given any f of x, given any y, finding f inverse of y is hard, right? Now this is what a one-way function is. It should not be impossible, because so the main point of locking your door is that it makes it difficult for anyone who doesn't have the key to open. Anyone who has the key should be able to open it easily, lock it easily, and open easily. But if you do not have the key, it should be difficult, right? So this is something that we do every day. You know, when you get out of your house, you lock your house, lock your room, and go, right? So difficulty, hardness, hard and easy is something that you're used to in life. And I'm pointing out that every time you log in, whatever you're typing in is actually encrypted. Encrypted basically means application of convert it into some ciphertext. But that function that converts it from your plain text to ciphertext is a one-way function, because coming up with, taking it and applying the code is very easy. But without the key, for somebody watching the channel, you said you can't, from the channel, you cannot figure out what your password is because it is encrypted, basically because finding the inverse is difficult, right? Now, how do you find one-way functions? Do they grow on trees? Well, they actually grow on trees. They're very, very simple things, right? Because, well, here is a question. Well, is 143 a prime number? Quickly, somebody tell me. Anyone? Well, too late, I'll read. What is 13 times 11? Anyone? So 13 times 11 is 143. So, yeah, I think somebody just managed to get it. Yeah. So 13 times 11 is 143. And so 143 is not a prime number. It has got two factors, two prime factors. And this is a fundamental thing, that if I give you two prime numbers, multiplying them is easy. But if I tell you a number, I even tell you that it's a product of two primes and ask you to find the factors, it's hard. Hard in what sense? And that's the point, right? Hard for me, for you, for which computer? Well, we are talking about problems that the fastest computer that we know today are not able to solve efficiently. And that's what we need. Now, we don't expect that factoring is hard forever. We believe that maybe there are efficient ways, we just don't know. But what about, here is another problem. So basically, what we want to do is, understand what is hard and easy in a sense that is technology independent. Then we can actually categorize problems as hard and easy. Like the dal, potato, chicken, we want to come up with a classification of problems as one being easier than another to solve. Now, this idea of solving things in this fashion, maybe one more question is worth it. We have to start counting, and like Ada Lovelace talked about, we have to multiplication. So here is a question involving multiplication again. Suppose I want to find out 5 raised to the 100. Right? It's a large number. Now, how many multiplications do I need? I want to find out 5 power 100. How many multiplications do I need? Does anyone want to tell me?
99 times.
99 times for sure, right? That will surely give the answer. Thanks, Jami. Now, yeah, but can I do it faster? 99 multiplications seem too much for me. Can I do it with fewer multiplications? Yeah, 99, yes, for sure. Thanks, Sapna. Anyone else wants to give me fewer multiplications?
If we subdivide 100 to the 50 to the power 2?
Yeah. How will that help me? Yeah. That's a good point. How do I use it? How many multiplications and how do I get it? Yeah. Okay, here is, watch this. This is very easy, right? With multiplication, 5 times 5, I get 5 squared, right? With 2 multiplications, I go to 5 squared times 5 squared, which will be 5 power 4. With 3 multiplications, I get to 5 power 8. 4 multiplications, I get 5 power 16. 5 multiplications, I get 5 power 64, 5 power 32. Now, 6 multiplications will give me 5 power 64. And I already have 5 power 32 in this one. So I multiply 5 power 64 and 5 power 32, I get 5 power 96. And I've done 7 multiplications. 5 power 4 was here in this finger, and I multiply 5 power 4 and I get 5 power 100. I need only 8 multiplications. I do not need 99 multiplications, I need only 99. So when Ada Lovelace says, we have to look at the order of operations and we have to count the we have to consider the abstract nature of the number of operations required. Required is the key word here. 99 multiplications will do, but how many are required? And I am saying that 8 multiplications will do the job. In general, if I want to find 2 power n, 5 power n or k power n, I need only log n base to the 2 multiplications. Now, if you're talking about n minus 1 multiplications, you are saying linear number of multiplications. I'm talking about logarithmic number of multiplications. That's an exponential improvement, right? And that's a huge improvement. So when we say easy, we are talking about things where if n is the size of the input, right? Now, n is a number here, right? That number, how many bits do you need to represent that number in the input? Log n is the size required. So in terms of the input, I want it to be linear or polynomial in the size of the input. So my log n number of multiplications is linear in the size of the input. If I were using 99 multiplications, if I'm doing linear number of multiplications, that is exponential in the size of the input. So one thing that mathematicians have come up with over a long period of time is that polynomials compose easily, exponentials do not compose. So polynomial number of operations we will consider easy. Anything that requires exponential number of operations is hard. That's a technology independent way of distinguishing hard and easy. Now, in the case of 5 power 100, we have argued that it's actually easy in terms of how many multiplications you need. But you need space to write it down, right? Suppose I want to find out 5 to the 100 mod 7. That means what? I want to find 5 power 100 and I want to divide by 7 and actually take the remainder. The remainder is going to be between 0 and 6. Now, but 5 to the 100 is such a huge number, I may not even have space to write it down. Do you know how many digits it has? It has a huge number of digits. But then I can use the same algorithm of squaring to reduce the space as well, because I want to find out 5 power 100 mod 7, that is 5 power 96 mod 7 times 5 power 4 mod 7. Each is a number between 0 and 6. And to find out 5 power 96 mod 7, I have to find 5 power 64 mod 7 times 5 power 32 mod 7. So it's always 0 to 6, so it's easy to write down. So this one I will really call it easy, not hard. Right? And why did I take this q power x mod n? That is in fact the one-way function that is used when you log into your Gmail account. Every time you are using any login, remote login, it's enabled by the Diffie-Hellman encryption algorithm, where the one-way function used is q power x mod n. And all this easy and hard that I'm talking about is not some abstract nonsense. It's, think about it. As we speak, every minute, there are billions of logins happening, right? And the underlying architecture uses Diffie-Hellman encryption and uses q power x mod n. And they're using this fact that given x, knowing q and n, which are public, finding q power x mod n is easy in the sense that I mentioned. But looking at this result, finding x is hard. It is hard. And in fact, we don't know of any computer. In fact, it's a one of the most beautiful major open problems of computer science to know whether this problem is solvable fast at all or not. We don't know. We believe that nobody can solve it. No super duper technology can solve it. One of the classic open. So, but these considerations go way back. The very word algorithm is from the 9th century Persian mathematician was this beautiful long name, Abdullah Allah Muhammad ibn Musa al-Khwarizmi, and an amazing mathematician from so long ago, 9th century, right? And he was trying to talk about, in fact, algebra comes from his book, which is about resolving conflict, what we call balancing equations. Until recently, the word algorithm referred exclusively to pencil and paper methods for numerical calculations. After computers came, we use it for this. And in fact, people trained in the reliable executions of these methods were actually called computers. When Alan Turing was writing about computers, he was talking about human beings. Those days, there were advertisements for people, largely women, who would use log tables and do calculations, and they were called computers. And the word computer comes from the Latin word putare, which means to prim or prune, to clean, to arrange, to value, to judge, to consider, suppose. So all these are, the word computer and algorithm already carry very important cultural and historic significances that we should remember. Now, there is a classic algorithm from the Rhind papyrus, which is the 19th century BCE. How many years that I'm talking about? This is not 19th century 2 years ago, right? This is 19 centuries before Christ, right? Long before Indus Valley civilization, long before anything we know of India. And the Rhind papyrus algorithm was the following algorithm. To multiply, I'm saying it, of course, in modern notation. If you want to multiply two positive integers n and a, it says, this is what you do. If find out if n is equal to 1, simple, 1 times a is a. Otherwise, if n is even, divide n by 2 and multiply a by 2, multiply it with 2. So this is very interesting because supposing I wanted to multiply 27 times 15. Well, in this case, n is odd, so minus 1 say. In that case, you add a and then 2, whatever you've got. So 13 will be, 27 by 2 is 13, 13 times 30. To find that, you find 6 times 120, and you keep adding 15 by this side, right? That is even, so 3 times. Now, what is going on here? One number keeps decreasing, another number keeps increasing. So what do you do here? So keep whichever is the smaller one constant, keep multiplying that, and the bigger one keep on dividing by halving it, right? This is a beautiful algorithm, and as I said, this comes to us from 4,000 years ago, right? And this is not an algorithm that is taught in our schools, right? But this is something that comes from 4,000 years ago. Now, this breaks the what does it do here? It breaks the difficult task of general multiplication into 4 simpler operations. First is to determine parity. If it is 1, otherwise you check if it is even or odd. Now, this is something very small children are taught right from the beginning. How do you find out if a number is even or odd? It's something very simple. Try to pair it up, and if you can pair it up, it's okay, it's even. And if you can't pair it up, one thing is left, then it's odd. But that intuition goes very far. All you have to know are a few odd numbers. In the last digit, you just have to know which are the odds and the evens and 0, and you are done. The next thing is you have to add. Okay, hopefully addition is simpler than multiplication. And the other thing is doubling, right? Doubling and halving, which is certainly simpler than general multiplication or general addition, right? And then, so this thing of mediating, having a number, rounding down, like 27 by 2, I said is 13, right? This is all, it's a few things you have to learn. But it's already breaking up a complex task into simpler tasks and composes them, right? So Rhind papyrus is something that should tell us that human beings have thought of this idea of algorithms all through, right? All through for commerce, for trade, people have been using algorithms. Now, I did a study in late 1990s when we were working with the learners of adult education in villages in Tamil Nadu. And we found that people were using all kinds of algorithms for estimating the yield of a field, harvest, for contracting, for many things. And very, very clever algorithms were being used by people in this, and many of them handed down across generations. Now, how do you show that the Rhind papyrus algorithm is correct? There is a recursive identity. What you are saying is that if I take non-negative integers x and y, x times y is 0, any one of them is 0, and otherwise you take the, if it is even, well, you just divide by 2, and well, I think this is pretty simple. So let me not go down. Here is a slightly different question. So this is a classic algorithm. Now here is a recipe that I have got to either become a millionaire or to become a pauper. You place some amount of money, say X, on the betting table. A fair coin is tossed. If it comes up heads, you lose your X. If it comes up tails, you get 2X. You get your own X and another X. Now, here is a rich man's strategy. Initially, he'll place 1 rupee on the table. And now what will happen? Well, he may lose or he may win. Of course, if he wins, he'll get 2 rupees. Right? Initially, in general, at any stage, if he loses X, he'll again play with 2X. At any time he wins, he will stop and go home. Is it clear? The story is clear? So here is a question. Does this constitute an algorithm for the rich man to become a millionaire? Or whichever. Or does it constitute an algorithm for the rich man to become a pauper? Pauper means poor, and going to walk out with money in one hand. Does anyone want to try? Yes. No? Well, we do not call it an algorithm because there is no guarantee of termination. Right? Now, you can say that the probability of this going on forever is very small. Right? And yeah, somebody says, no, it's not an algorithm. And yeah, it's not an algorithm because of a very simple property. We want to, for all inputs, we want an algorithm to terminate. And we are not talking about probabilistic guarantees here. Right? So this is what distinguishes algorithms from other methods. With that, we want a recipe that will succeed on all inputs, and we can prove that it will do so. Right? This is one of the fundamental characteristics of algorithms. Of course, there's a very interesting question. What's the probability that the gambling will eventually happen? If you say K steps in terms of K, can you give me a bound on the top? That's an interesting question. I'm not taking that. So the main point is that we require that algorithms be correct for all possible inputs. We must prove that our algorithms are correct. And correctness proves almost always induction, always involve induction. We have to formally state what that algorithm is supposed to. And it's important to distinguish the distinction between a problem and an algorithm. That is, when many students, I start talking about a problem and they start, trying to solve the problem or give the algorithm. And that's very important to actually distinguish the two, right? If I want to sort some n numbers, right? Input is n numbers. Now, what is the specification of the sorting? I don't want to know how you sort. I just want to tell me what is the relation between the input and the output. Now, if you just say that all elements, I want to put it in ascending order, right? If you just say that the output that you give is in ascending order, if that's a contract you give me, I'll just write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's an ascending order, right? Now, it's not correct to say that the specification is extremely important. And you want to say that the output is a permutation of the input. There are no extra elements, no elements have been lost. It's exactly a permutation of the input, and it is in ascending order. Then you have a specification of a sorting problem. So this is the distinction between. So you need to say what it is supposed to do. Then only you can verify that your algorithm is doing what it's supposed to do. In fact, often the hardest part of answering any question is figuring out the right way to ask it. And this is not an easy question. Formulating in the problem in such a way that you can actually come up with an algorithm is actually not easy. And this is something that we don't really teach our students, and our students don't get much of an opportunity to think about this at all. That's why I mentioned it. So ideally, we want the fastest possible algorithm for any particular problem. Fastest, I would say, using the best resources, using your resources most efficiently. If you take time as the resource, you want it the fastest one. If you take space as the resource, you want to be as economical about space. So we require algorithms that always run efficiently, even in the worst case. This is something that our students almost never remember, that any planning that you have to do, you have to look at the worst case possible plan. You can't say that mostly my input will be something like this and this is what I do. And that's simply not acceptable. Question is, how do you determine which is the worst case instance? And this is a skill that you have to learn. And I would say one of the important purposes of learning algorithms is to learn to start looking for what is the worst case instance. It helps very helpful in life as well in terms of planning, in terms of organizing. Question is also, how do we measure running time? You don't have technology available. Maybe time will be different on different machines. That's why you have to learn what is it that you count and how do you count it? And number of comparisons, number of additions, what operations am I counting? And how do I measure it? Sometimes we are also interested in other computational resources like space, randomness, because sometimes you have to flip a coin, how many random bits I'm using, page faults that can occur in memory, interprocess messages, and so forth, where the techniques are similar. And especially in distributed computing, you measure the number of messages that are exchanged, length of messages. So different resources, different ways of measuring may be there for different kind of algorithms, but the core technique is this. And what I'm pointing out is that these are the skills that are very important for us to learn. Not about particular algorithms, not about statements about particular algorithms. We need to be able to ask such questions and formulate answers to them. Right or wrong can come later. Now, I wanted to take up an example, and there is a beautiful problem called stable matching, and I'm not going to take it up now. I'm going to skip that entire analysis because we are out of time. But I wanted to show you, I mean, you can take almost any algorithm and you can see how the analysis goes. And how do you get worst case? How do you analyze worst case? How do you prove correctness? And even after you prove, there are questions about quality of solutions. How do you do better? And a lot of analysis. And this is what is extremely important and the kind of techniques that we learn. Okay, so I'm skipping this whole analysis for you. Now, main point is that in algorithms course, we pick up a bunch of algorithmic facts. For instance, merge sort runs in, theta n log n time. The amortized time to search display tree is order log n. Greedy algorithms don't produce optimal solutions. These are all things that if you learn a good algorithms course, the traveling salesman problem is NP hard. Now, these facts are important, but they're not as important as the objective of the course is not to learn these facts at all. It's not the main point. In fact, Wikipedia can tell you any of these things. And you should use Wikipedia and Google to find out facts. After all, that's what we use for many things in life. The point is to provide enough intuition and experience to know what to look for, right? Is my algorithm, is it log n times, or is it linear, or is it exponential, is it n squared? How do I develop intuition into all this? How do I find the worst case, right? And what is the kind of case analysis I should be doing? Those is what I call intuition and experience of analysis. The study of algorithms it certainly does aim to provide practice in a lot of algorithm design and analysis skills. But then what we have to really learn are finding useful examples, useful counterexamples, developing induction proofs, solving recurrences. I use the notation like big O in one place, theta in one place. What does it mean? Where do you use probability? And how do I, like in the case of sorting, I said the output should be a permutation of the input and order. How do I give crisp mathematical descriptions of problems. Now, these are the kind of algorithmic skills that are extremely, and this is all incredibly useful for developing intuition, but this is not the main point either. So what then is the main point? The study of algorithms is ultimately about learning two skills that are crucial for all computer scientists. One is intuition, and the other is language. Intuition, how do you think about abstract computation? This is not easy, and this is probably the hardest thing that we want to know. We want to develop an intuition about how to look at some problem in the world, abstract away from the details of the problem that you see in the world, in a way that you can formulate as an abstract problem and solve the abstract problem, because that is when you can translate it into bits, into the abstract data structures, representations, and write your algorithms form. So we need to learn how to think about abstract computation, and we should learn how to talk about it. And talking about it is all this big O notation, order n log n, all this kind of, it's a certain language that you learn. And this, can it be taught? Can such intuition be taught? What does it mean to develop such? Well, you have to ask, how do various algorithms really work? When you see a problem for the first time, how should you attack it? How do you tell which techniques will work at all and which ones will work best? How do you judge whether one algorithm is better than another? How do you tell whether you've got the best possible solution? These are what go into intuition. These are not easy questions, but in some sense, understanding thinking of this kind, to me, is the objective of learning. So what is indeed the main reason to study algorithms? I started with this question, why should we learn algorithms? Why should we learn algorithms? The point is, coming to the second question, if you're a computer science student at all, algorithms, like I think was already pointed out by, I think, Internal Basu, I think, that this is what makes it a science, right? This is what makes it technology independent. The fact that sorting takes order n log n time and will require n log n time will stand. In the 23rd century, somebody talking about algorithms will use order n log n time, because you cannot do that. This is a mathematical statement, right? This is a technology independent statement. That sorting is harder than searching is a statement like the dal and the potato, right? And both of them are easier than factoring a prime number, factoring a composite number, right? Now, these levels of difficulty, understanding this in a technology-independent fashion is what makes it a science. And this insight, learning to look at the worst case, learning to develop, developing this intuition is important for life, is important for all of computer science. That's why we call it a compulsory subject, and we say that it doesn't matter whether you're going to do HTTP or whatever you're going to do in life, this is something that is core. So that is the answer to the why should we learn algorithms. And should we learn algorithms at all is because it teaches you a way of thinking, and it is a way of thinking is the very important reason. So good algorithms are extremely useful, elegant, surprising, deep, even beautiful. Learning algorithms teaches you a way of thinking, an approach to step-by-step reasoning, and an idea of scaling. Scaling something that works for 20, when it works for 2,000, hundreds of thousands, without worrying. Most importantly, of course, algorithms are fun. If you ask me, ultimately that's the most important reason why I would want to continue with algorithms. Thank you. Yeah.
Thank you so much, sir. Thank you so much. But I would like to request all that if you have questions, you kindly raise your hands. I can immediately unmute you. For questions, kindly raise your hands. Or you can simply unmute yourself also.
May I ask a question?
Yes, please go ahead, sir.
Yeah, I just want to ask the way you are suggesting that it is technology independent. the computation of the algorithm will be technology independent. But with advent of things like quantum computers, don't you think this assumption itself is in question?
No,
That
no. Let me be clear about it. The computation itself is not independent, right? That's why I said the computation is of course dependent on it, but we are making certain statements about the computation that are independent. Like for instance, n log n is a lower bound for sorting is completely technology independent. Whether it's a quantum computer or whether it will take n log n time, right? Now, whether n log n time can be realized is a different story, right? Now, when it comes to computability itself, right, in terms of what is computable and not computable, is something that whether it's a quantum computer or whether it's a classical computer, it's the same, right? When it comes to computability, it's all the same. In quantum computation and classical computation, what is the distinction that we are seeking, we don't know, but we are hoping or seeking, is problems that could take an exponential amount of time on the classical machine can be done in polynomial time on the quantum computer, right? And that is something that we want to. And for instance, if you talk about DNA computation, you want to use parallelism that depends on n itself. And if you can have exponentially many processors available, you can even compute these in linear time, right? But then the product is still constant. I hope that's clear, right?
okay.
So in quantum parallelism, what you are talking about is exponentially many, in quantum evolution, since you can have all these qubits available to you. So what you're effectively using exponentially many processors available to you, and therefore you're able to do something in polynomial time. But if you take the product itself, it remains exponential. I hope I'm making it clear.
Yeah, okay, I've understood. Thank you very much.
Now, relative to that, I have one question. Can I go ahead?
Yes, please. And
Yeah.
but I have a question for you also.
Okay.
Shall I ask you first? Before?
Yes, please. Yes, please.
I'm very curious to see your the screen that you use for your.
Okay, that is the
this
electrical. That is the electrical engineering.
I know. I
Not electrical, it's signal processing actually.
Absolutely.
Electronics.
Yeah, for transient. I wanted to know why you use this for your thing. And it's
I would like to change it. I fancied it once upon a time.
No, but it's a beautiful graph. So I'm very happy to see it. Yeah.
Because transients, I was very curious about transient phenomena in electrical systems.
No, and that's a beautiful thing to do.
Yeah. So actually, I read in a computer science website of a U.S. university, Oberlin College, actually in Ohio.
Oh, yes.
In the computer science website, that the computer to computer science, it has the same relation as a microscope to biology. Like microscope is not inherent to biological sciences; it's a tool. Just like computer is a tool to pure computational science.
Oh yes, absolutely.
So your comments, please.
Absolutely. Actually, this kind of comments are, go all the way back to Galileo Galilei, who he said, a telescope is only a way of looking at the heavens, right? It is the heavens that are the stars, and they are important. They are the ones that you are studying. The telescope is only a tool. So, of course, it enables you to look at things, but it's a distinguish the tool and actually the object of study. Yeah. So, and since then, of course, many people have said, and I completely go with that. I think we have to think about the computer as a tool to study problems in life. What in computer science you study is not the computer at all, but problems in life. And that is why we talk about ubiquitous computing and why this device is so incredibly flexible and has gone across all aspects of modern life. Because what we study are not computers, but problems out there in the world which we can computerize, mathematize in some sense. Yeah, it's the same spirit.
Thank you.
Thank you, sir. Any other question that anybody would like to ask?
Yes, sir.
Yeah,
Yes,
go ahead, Devasmita. Go ahead, Devasmita.
So how can we interface between quantum computer and classical computers?
That's, I don't think anyone knows the answer to that question. I certainly don't, and I don't think anybody knows. Because this is one of the fundamental problems, and quantum computation
Means,
itself.
is it possible actually?
Who knows? I mean, it's no way to show that it's impossible either, right? And that's the point. The thing is that, okay, one thing you should understand, forget computation. There are any number of devices, quantum-based devices that we have, right? So, we do read off. I mean, there is this beautiful picture that IBM came up with at the level of, writing your name at the level of atoms. Right? Quantum cooling, quantum Hall effect. So there are any number of devices which can read off. So it's not something that is theoretically impossible, but what we don't have is actual means of doing it. So, and there are all kinds of limitations involved, but there's nothing that stops you in principle to say it's impossible. So, I'm asked, but actually whether we can actually do it or not, who knows? Yeah.
Okay, sir. Thank you, sir.
Yeah.
Thank you,
Sir,
sir.
I want to ask a question.
Yeah. Yes, please.
Sir, we know that there is a research going on artificial neurons. So how do you think that the algorithms will help us to understand that how artificial neurons works?
Yeah. So their techniques, they are asymptotic algorithms. I mean, in fact, in terms of their correctness, what you can only show is that you put a bound, run the artificial network, the ANN network, certain number of times, and within this bound, this is what it computes. And we can give definite guarantees for that. It is in this sense. But I agree that there are correctness questions that are fairly not easy out there. That's the problem with neural network-based algorithms, is that we don't have good explanatory power. I mean, we can do many things, but we are not able to explain why it works or how it works, and and very important issues related to stability. One of the things that I had in the matching problem to discuss was the stability of solutions or stability of algorithm. Now, one thing that you would like, if you take a sorting algorithm, that it's stable, in the sense that if I perturb the input a little bit, the algorithm doesn't change. Unfortunately, for ANN-based algorithms, neural network-based algorithms that you're talking about, for one input, it gives a, let's say it recognizes something, and if I perturb the input just a little, it may recognize it to be something completely different. So now these are things that people are working on, but there are problems, fundamental problems that are. Somebody is asking a question about how private are private algorithms. Yeah, almost all all guarantees on related to privacy are probabilistic, and so cryptography, all not just practical cryptography, theoretically also.
Sir, how algorithm helps in CNN?
Okay, first let me finish on privacy. Is that these are all probabilistic guarantees, and when we talk about very small probability events, we must remember they do occur and can occur. And when you talk about 1 in a million probability, that sounds very, very good, right? And error probability is 1 in a million. But if you have billion logins happening every minute, 1 in a million is not really very private, right? So this is the kind of problems. And so unless you go into the mathematics of it a little carefully, we can miss a huge amount of detail. So the short answer to your question is that almost all privacy claims that we read about have to be looked at with a lot of healthy suspicion and subjected to fine analysis. Yeah. So here was this question. You had a question. I'm sorry, I missed it.
Sir, how algorithm works in case of CNN, convolution neural network?
That is, firstly, I don't know if I'm competent enough to answer. Secondly, that's a whole lecture on its own, right? Because convolution is a process that we have to understand, right? But I must say that they do not lend themselves to the kind of analysis that I was talking about. Once again, the kind of proofs, termination proofs, the correctness guarantees, worst case inputs, all of it is problematic. But it's something that one should take up.
Okay, sir.
Sir?
Yeah. Yes, please. Yeah, go ahead and ask.
For placement algorithm.
What is the question again, please?
For the placement purposes, how can we prepare algorithms?
Yeah, so there it's very clear to me, at least from what I hear from let's say that people from Infosys or GPS, or Google and big companies, right? They are very clear that they are not interested in specific computing skills. If your skills are mainly platform dependent, right? If most of my computing skills, software skills are on specific platforms, as the platforms become obsolete, your learning can become obsolete as well, right? So most of the people who are looking for people for programming skills are really looking for algorithms, right? If you can show any kind of algorithmic skill at all, it's not important that you should know lots of algorithms. That's why I kept saying that. You don't need to know. But even if you're talking about one algorithm, like I talked about the Diffie-Hellman encryption, it doesn't matter. But if you can look into the details of it, know it in depth, be able to look at worst case, look at how to change the algorithm if there is a change in specification given to you, that would be considered much more important marketable skill. Mainly because people are looking at your problem solving ability, and for problem solving ability in an algorithmic sense is what they're, at least this is what they say. And in fact, there is a very interesting incident about 10 years ago, I think. The big majors in Bangalore got together and submitted a memorandum to Bangalore University saying that, for computer science students, don't teach a lot of platforms. We do have our own training. We can train them on platforms, teach them fundamentals, right? And this is something that Infosys took the lead on. And it's very much related to what Shangri has right now, that they're really looking for problem solving skills.
So, is there any other question?
Because yes, sir, I had a question, sir.
Yes, please go ahead, Professor Amit.
Okay. Sir, I want to ask you one question. What your personal view on the career, near future career as a quantum computer scientist?
Yeah, I mean, it's the next big thing, you must say, in terms of research. In terms of research.
Means what I want to say you that what is the means what is the degree of feasibility in implementation of physical quantum computer?
See, we look at the history of computing, right? I mean, Neumann in 1945 working on the UNIVAC and ENIAC that was being built, right? They found it very hard to build a machine with, I think, 512 bits of memory. Right? And Fortran was created on a computer which had like 1K bits of memory. And and Fortran was one of the most powerful ways of doing programming. What we are looking at with qubits in quantum computing is in a situation like that today, right? 64 qubit machine is what the Cambridge collaboration has managed to do, and the Berkeley collaboration consortium is also talking about of the order of 100 bits. But this is a technological barrier, right? If there is a breakthrough, things will move very fast. And once again, let me say there is no in principle barrier right now for these barriers to be broken at all. Government of India is in fact also invested in a huge project, the quantum computing initiative. So world over, and the Chinese have invested some major. And the barriers are all technological. There is no in principle barrier at all.
Yes, sir.
And what we don't know is how to write programs for your content, how to develop algorithms for that. Mainly because, like somebody talked about, the interface between classical and quantum is something we don't understand. We don't even know how to prepare the input and how to read the output. And how to see, one of the important things that computers will use is that programs call each other, right? The output of one program is fed as input of another program. Without that, you can't have compilation with the operating system. You don't have anything. That composability is a deep problem in quantum computing because it will carry memory, it will carry trace of the earlier computation itself. So how do you forget all that and restart? We don't know any of that. So we are very far away from general purpose computation. But in terms of research, I think it's a fantastic area of research and something that brings together people from the natural sciences and physical sciences.
Okay, thank you, sir. Thank you.
Sir,
Yeah.
what should be the approach to do some research work on algorithm? Like how we can make our algorithm more efficient?
Yeah. So for that, as I said, almost any algorithm that you can pick up, any of the kind of questions that you can pick up, you can raise that, and that's really not a problem. I would say if you look at a book like Corman, Lysensen and Rivers, CLR, that's a good enough. It's a fat book, but it throws many challenges at you, and you can try to solve. It's not difficult. It's more about getting into a certain way of thinking. It's not about you have to get out of looking at particular examples and working on examples and being able to, you want to look at the general case. You want to get techniques for solving recurrences. Then you can fly really fast. So learn induction proofs, learn a few things like that, and learn to look at worst case counterexamples. Then you're in business.
So if you would suggest a platform like to approach algorithms and study it, like
Yeah, there is a thing called Algorithms Workbench, which maybe if somebody sends me mail, I can send a link, and things related to that. There are pretty good tools available there.
So can you repeat one, sir?
It's called Algorithms Workbench.
Yes,
this was developed by the Max Planck Institute in Germany, but it has now seen many versions all over the world. That's a good tool. But probably there are others that I don't know about. This is something that I know about, which is good.
Sir, my question is related to placement, but I think it's a good question. Sir, as we are computer science student, we should learn algorithms, but in point of for placement point of view, we should also learn some technologies. But if our target is to get a job in our dream companies, they just follow. They need to learn algorithms. So because they have good technologies, and after getting a job, they will train us to use that technologies. But there's just a trade-off that if we want to play a safe side, learning some trending technologies, or
no, I agree that you need a combination. I'm not qualified or competent to talk on the engineering side, so I'm talking more on the side that I understand. But certainly, I agree that you need a combination of skills. If at all I'm pushing for this, it's only because this is so undervalued and so underemphasized that it's easy to overemphasize the tech, scientific aspects. That's why I'm. But I agree that you need a balance. Anything else?
So, is there any other question from anybody? There is a question in the chat box, though. Sir, Prithishwar Bhattacharya has written, "Sir, does space science have any relation?"
Oh yeah, I forgot. Yeah, I saw that. Yeah, does space science have any relation with computer science? Well, I don't really know the answer to that question, but I do know that ISRO is perhaps one of the major employers of algorithm specialists today, because they have algorithmic problems with real-time deadlines. I mean, talk about satellites and their navigation and these are not general algorithmic problems, but algorithmic problems, what they call deadlines. And related to the field of real-time computing, where your answers have to be produced fast. I mean, really, really fast. So they also work in an area which is called algorithm tuning. And that's a fascinating and beautiful field that most people don't know about, where you want to take existing algorithms and fine-tune them for these kind of requirements, where your requirements are like, something that normally people you don't even think about. You're not interested in the running time. I want to make sure that the hardware that uses it minimizes energy, right? I want to minimize heat, right, in the running of my computation, right? How do I tailor algorithms in such a way that when I run it on my hardware, the heat generated is minimized? ISRO has requirements like this. So I know of some beautiful cutting-edge research questions that many people work on this kind, but direct relation that you ask, I have no idea. But I know that. Nice questions there. Okay, then I think.
I believe there are no more questions, sir, because if there is any question, somebody can ask. So really, it was really a wonderful, wonderful session, sir. We really got to learn many things. And most importantly, I feel that you have opened many domains for many of us to think and proceed in that direction. I'm sure that the students got a lot of energy to maybe think of research in algorithms. Maybe the best field to do research. You can never end. You can get problems after problems after problems and keep on doing research. I will encourage all my students, your alumni, your seniors are doing great in that. And I'm really happy that you asked a question. I think Shagorika also asked some question like that. So that is good that you have thought in that line. And sir, thank you that you have actually motivated us to think so. Shankhodip, do you have anything to add? Because Shankhodip is our alumni, sir, of University of Engineering Management Jaipur. So Shankhodip has initiated this whole thing. So Shankhodip, do you have anything to say over here? Just to end it, Shankhodip, are you there? I think he's having some problem because.
Yeah.
Okay. Yeah.
Yeah. Am I audible?
Yes, yeah. You're audible.
So I think this was a wonderful session because of the interactions from both the students and faculties, and also from the end of Professor Ramanujan. And I would like to thank Professor Ramanujan from the core of my heart, and also on behalf of UEM Jaipur ACM Student Chapter, to accept our kind invitation. And yes, and last but not the least, thanks to all the participants. Thank you.
Yeah. Thank you very much. I should also especially thank Shankadeep, because I insisted that we should have interactions, and he assured me, and I'm very, very happy with making the effort for that. Thank you. Because,
thank you.
This online medium, webinars, it's really, can be like talking to a wall. The point is to generate discussion.
Right, sir. I agree. I absolutely agree with you. Thank you, Professor Shovik. Thank you so much, Professor Mrinal, Professor Rupayon, and all other members who are associated with this. Yusuf, Jamil, Jyotirmoy, I don't know whether he's there, and many other members, Maneval Dreek, many other members of this ACM chapter. I think Dev Smita, Shagorika. Thank you so much. And thank you so much, sir. Thank you so much.
Thank you
so very much. Thank you. We are looking forward to meet you again in Jaipur sometimes after this.
Thank you, sir.
Thank you, sir, for your time.
Thank you so much.
Bye-bye.